Hello, check. Hello.
Hi everyone, welcome back to ICTS String seminar series. So for today's seminar, we have Moumita Patra, and she will be talking about aspects of n equal to 3 Chern-Simons Quiver gauge theories with ADE classification. Yeah, over to you, Moumita.
Okay, so today I'll be talking about some aspects of n is equal to 3 Chern-Simons Quiver gauge theories with ADE classification, and I'll be talking about how to compute these two quantities in these theories. The first one is the non-abelian R charges of the BPS monopole operators in the theories, and then I'll compute the superconformal indices for the same theories. Okay, so let's first start with the first part, which is the non-abelian R charges. Okay, so before getting into the details, let me just quickly describe the motivation and logic behind our calculation. So we want to compute the spectrum of conformal dimension of monopole operators for in n is equal to 3 Chern-Simons Quiver gauge theories. To do this, we follow the method outlined by Benna, Klebanov and Close in this paper, who has done the same computation for n is equal to 6 Chern-Simons theories with gauge group UN cross UN. This theory is widely known as Ebgm theory, which is a three-dimensional theory with n is equal to 6 supersymmetry. And there's a Chern-Simons level K in the theory, and the symmetry, supersymmetry of the theory can be enhanced to n is equal to 8 for the values of the Chern-Simons level 1 and 2. So now our goal is to generalize the method introduced by BKK for more than 2 gauge groups. So let me first describe how it is done in BKK. So we want to find the spectrum of conformal dimension of the monopole operators in the theory, and the monopole operators exist in these theories. So now the only coupling parameter in Ebgm theory is the Chern-Simons level, which is denoted by small k. But for small values of k, the theory is strongly coupled. So it is difficult to do any computation for small values of k. But since the monopole operators exist in the theory for any value of k, therefore, we introduce a Young-Mills deformation to the theory. Now, the role of the Young-Mills deformation is to introduce a dimensional coupling G in the theory and provide a weakly coupled UV computation of the theory. So therefore, for very small values of G, we can do a perturbation theory computation and compute whatever desired quantity. So the trick is we carry out all the computations in the far UV, where the coupling parameter G is very small, and then flow to the IR fixed point where G is very large. And the conformal dimension is of course defined at the conformal fixed point where G is very large. Now, since we want to find the conformal dimension of the monopole operators, which is valid in the IR, and we are doing all the computations in the UV. So therefore, we need to compute some quantity in the UV that is related to the conformal dimension of the monopole operator in the IR and does not change along the RG flow from small g to large G. And that quantity is the non-abelian R charges of these BPS monopole operators. Since these charges are quantized non-abelian charges, therefore takes quantized values and does not change along the continuous RG flow in the parameter G. So in the UV, the monopole operators can be described by classical BPS solutions of the theory. And at the conformal fixed point, the R charges are related to the conformal dimension of the BPS monopole operators by state operator correspondence. So the first goal is to find a classical BPS solution in the theory and then find its charges. Okay, so this is the idea behind the calculation. Now the outline is as follows. So
from the R charges, you can figure out the conformal dimension.
Yeah, so from the we will compute the R charges because it is BPS. The BPS condition will relate the charges to the energy of the corresponding states, and after using the BPS condition, one can use the state operator correspondence to relate the which relates the charges to the conformal dimension of the corresponding states.
I see. So the R charges are the same in the UV and IR, but the conformal dimensions are different, you are saying. Is that right?
No, yes, I'm saying yes, the charges are the conformal dimensions. That's what I also.
And the relation is the same in the UV and IR?
IR, yes.
I see. Then the conformal dimension in the UV and IR should also match.
Yes. I mean, conformal dimension does not make any sense in the UV, right? It should be valid in the conformal
I see,
theories.
okay. Because UV is not conformal.
UV is not conformal.
I see, okay.
Okay. So this outline of the first part of the talk is as follows. First, I will construct a n is equal to 3 Chern-Simons theory in 2 plus 1 dimension. Then I will define what a quiver gauge theory is. And as I said, after that, we will introduce a Young-Mills deformation to the theory so that we can do our computations in the weakly coupled limit. And after that, we'll find a classical BPS monopole solutions in the deformed theory. And we'll find the charges of the monopole operators of the theory, which are described by the classical BPS solutions in the UV. And all these steps we'll do for a simpler quiver, which is circular, and then we'll generalize the same idea to D and E quivers. I'll explain these things. Okay. So how to construct a n is equal to 3 supersymmetric theory in 2 plus 1 dimension. So one way to construct a n is equal to 3 Chern-Simons theory in 2 plus 1 dimension is to start with a n is equal to 4 supersymmetric theory in 3 dimension. Now, so we need to look at the n is equal to 4 supersymmetric theory field content. So now n is equal to 4 theory in 3 dimension is a dimensional reduction of n is equal to 2 theory in 4 dimension. So the field content of n is equal to 2 theory in 4 dimension is as follows. It has 2 multiplets. First one is a vector multiplet, which contains a vector superfield, which is denoted by this curly V. And it has these component fields. Sigma is a real scalar field that comes after the dimensional reduction from the 4 dimension. Mu is a 3 component gauge field. Chi sigma is a fermion, and D is an auxiliary field. And there's a chiral superfield, which is denoted by bold phi. And it has these 3 components, complex scalar phi, a fermion chi phi, and an auxiliary field f of phi. And vector superfield and the chiral superfield are in the adjoint representation of the gauge group G. And there's a hypermultiplet which contains 2 chiral superfield, which is denoted by curly Z and curly W, and which has these component fields as said here. And they are in some representation R of the gauge group G. So if Z is in representation R of the gauge group G, W will be in the representation R bar of the gauge group G. Okay, so this is the field content of n is equal to 2 theory in 4 dimension. And now to obtain the n is equal to 3 theory from this n is equal to 4 theory is done by adding a Chern-Simons term to the action. So the final Chern-Simons action with n is equal to 3 supersymmetry has this schematical structure. There is a Chern-Simons part, which is denoted by SCS. And there's a matter part, which comes from the chiral superfields. And there's a superpotential term. Okay. So now let me describe what a quiver gauge theory is.
At this stage, you have not added the
No. This is the superconformal theory. Okay. So now whatever the field content I have described here can be represented by a diagram, which I'm calling as a quiver diagram. So it's a way to represent the field content of the gauge theory. So the field content of this ADE n is equal to 3 superconformal Chern-Simons matter theories can be summarized by ADE quiver diagrams. And these theories has a M theory dual in terms of ADS4 times M7, where M7 is a tricyclic Einstein manifold. Okay, now let me show a quiver diagram of A type. So this is the A-type quiver diagram, which is just a circle with some circular diagram with some circles and some arrows. These circles represents the gauge multiplet of the theory, which means there is a vector superfield and a chiral superfield in the adjoint representation of that gauge group. Now this N1, N2s are the ranks of the gauge group associated to the circle, and the colored subscripts denotes the nodes, the circles in that quiver diagram. And these arrows represents the hypermultiplets of the theory. As I said, there are two fields, two chiral superfields in the hypermultiplet denoted by curly Z and W, and they are in some representation under the gauge groups. So here Z1 is in the bifundamental representation of N1 and N2 because it is connecting N1 and N2. Z1 is a representation N1, N2 bar, and W1 is in a representation N2, N1 bar, and so on. Okay. So this is a circular quiver diagram, which is called A-type quiver diagram. And we have seen that how the field content of n is equal to 3 Chern-Simons matter theory can be represented by this quiver diagram. Okay, now let us first construct the action in the theory. So the action has these three parts, which is the Chern-Simons part, and the matter part and the superpotential part. These are the superspace actions of the theory. And from here, by using the component expansion of the superfields, one can compute the component action from the superspace action. Okay.
Moumita,
yeah.
The action seems to have equal to 4 supersymmetry. When, I mean, the way you have written the Chern-Simons action has 4 thetas.
No, no, no.
So namely, it looks like it can have a...
No, no, no. So this is actually, so without this Chern-Simons term, it is n is equal to 4. But after adding the n is equal to 2 Chern-Simons term, it breaks on supersymmetry and the entire thing is. So this the superpotential which comes due to the Chern-Simons part, it breaks on supersymmetry, and the net thing is n is equal to 3.
So the modification is in 2 places. One
Yeah.
is you add the Chern-Simons term.
Yeah.
And you add this W.
The Chern-Simons term will come with the superpotential of its. The K is sitting here, which is a Chern-Simons level.
But even then, you just look at the superspace expressions.
Yeah.
Everything looks supersymmetric.
Yeah, yeah, with n is equal to 4. Yeah.
Where is the because you do have a D2 theta. Is it that the WJ is not chiral anymore? If you add the contribution to the chart, still there's a chiral.
It is chiral. So I have checked the supersymmetry and it is n is equal to 3.
3.
Yes.
So somehow they're saying even though there are 4 thetas, and I mean, it looks like that those are B terms and these are X terms.
Yes.
As if you have n equal to 4, right? So which part do you have to remove to get n equal to 4?
The Chern-Simons part, this SCS and this superpotential as well, we need to remove. Then it is n is equal to 4. But it has been shown to have n is equal to 3 supersymmetry.
Only.
Yes.
Not 4.
Not 4. Okay. Okay, now let us deform the theory by introducing the Young-Mills deformation, which is done by adding the last 2 terms, S Young-Mills and S adjoint in the theory. So these equation 1.8 and 1.9 are the superspace expressions of the deformations. So this G square is the Young-Mills, G is the Young-Mills coupling, which is introduced by this deformation. And we can see roughly that when G is very large, these 2 terms drop out from the action and we can get back to the original theory. And when G is very small, these 2 terms are the dominant terms in the action. So now the deformation is done. Yeah. Okay. Now we need to compute the classical BPS solution in the theory. For that, we need to have the full component action in the theory. So before writing the component action, Since we are interested in finding the R charges of the monopole operators in the theory, we need to write the superspace action in a way so that the R symmetry is manifest in the action. For that, what we do is we arrange all our component fields of the theory in some representations of R symmetry. So in this case, the R symmetry group of the theory is SU2. So we arrange all the scalar fields of the vector multiplet in this 3 of SU2, which is denoted by this 2 by 2 matrix phi AB. And all the fermions of the theory are arranged in this 2 by 2 matrix lambda AB, the adjoint fermions. And similarly, the hypermultiplets are also arranged in terms of this SU2 or doublets of the theory, which is denoted by X dagger, which contains the scalars of the hypermultiplets, and xi and xi dagger, which contains the fermions of the hypermultiplet. Okay, now we write our component action in terms of these R symmetry multiplets, not directly in terms of the component fields. So this is the kinetic part of the action, and this is the interaction part of the action. From here, we want to find a classical BPS monopole solution of the theory. For that, we write down all the supersymmetry variations in the theory. So these are all the supersymmetry variation. Since we are interested in a BPS solution, we make all the fermionic variations of the theory to 0 supersymmetrically, which means we need to make the order 1 by G term and order G term in delta lambda AB to 0 separately. So we are interested in finding a monopole solution in the theory. So we start with the gauge field configuration, which is a Dirac monopole field configuration given in equation 1.14. And we substitute this expression of A in delta lambda AB in the fermionic variations and equate them to 0 and order by order in G. By doing so, what we see is we need to turn on an additional adjoint scalar field phi so that we get a supersymmetric BPS solution of the theory. So the equation 1.15 is the BPS background of the theory. So there is a gauge field and there is an adjoint scalar field. And this solution preserves only 1/3 of the supersymmetry of the theory. So now we have found the BPS, classical BPS monopole solution of the theory. Now our goal is to compute the R charges in this background. So for that, first what we do is we generalize our solution for the scalar, which we chose as delta I3, which means we chose in the particular direction in the R symmetry direction, which was 3. But since we have full SU2 R symmetry in the theory, we generalize this U1 background to this, which is denoted by -h/2 Ni tau. Ni tau is a unit vector on the 2 sphere, and it is called the collective coordinate of the BPS background. Now, since SU2R is a global symmetry of the theory, it will act on the scalar fields phi I.
So tau is the time.
Tau is the Euclidean time. Euclidean time coordinate. Now, the action of this SU2R global symmetry is to rotate the unit vector on the 2 sphere. And since SU2R is a symmetry of the theory, and there will be a conserved quantity associated with this action, and that quantity is the our desired BPS monopole charges. Okay, so since this scalar is not free, it is interacting with the fermions of the theory. So to account for the interaction of the fermions, we need to find the effective action in that background of the collective coordinate, which is done by computing the effective action in equation 1.18. And we need to remember that we are working in a limit where G is 0. And in this limit, only these interaction terms survives that interacts with the collective coordinate n tau. And after doing this functional integration, what we find is that the effective action is that of a free particle, which is moving on the surface of the sphere. So there is no interaction left, even though it was interacting with the hypermultiplet fermions and the vector multiplet fermions. So this cancellation basically happens, there's a cancellation which is happening between the hypermultiplet and vector multiplet fermions. It precisely cancels the interaction terms. So what we get is the action of a free particle on the sphere. So
M is some calculated number.
Yeah. So M is
So
this.
that will get from some determinant.
Yes. So we need to substitute this answers for the gauge field and the scalar BPS background. We substitute in the action, and then we do the one loop effective action, and that's what we find. Now it's a free particle which moves on a sphere. So the conserved quantity is the angular momentum, and its quantized values are that of a free particle moving on a two sphere. So it starts from 0. So we have seen that this is the spectrum of the conformal dimensions of the BPS monopole operators. And this result matches with the Ebgm theory as well. In the Ebgm, the field content was such that there was a cancellation of there's a cancellation between the hypermultiplet and the vector multiplet, and we also get the same result. And which it should, because when we just take two nodes instead of j is equal to 1 to n, if we restrict it from j is equal to 1 to 2, we should get the result should match with the Ebgm theory. Okay. So now we can generalize this same concept for the other quiver theories as well. So we started with the circular quiver. Now we can generalize the same idea to other quivers. So this is a quiver which is called a D-type quiver, and it looks as follows. So these nodes, the external nodes, I'm calling them external nodes, and these are the internal nodes. So these internal nodes are like A-type quivers only. Only these two nodes are a bit different because they are attached to 3 hypermultiplets. But and the gauge group of the theory is u2n to the power n minus 3 and un to the power 4, and n has to be greater than 3. So this is a D-type quiver diagram, and similarly we can redo the entire calculation for this quiver as well. That is finding the BPS monopole solution of the theory and finding its R charges. So it's again done by computing the component action and finding the BPS solution. So now here, because we have gauge groups of 2 different ranks, we need to start with 2 different Dirac monopole-like answers, which is given in equation 1.23. And H1 and H2 are, H1 is a n by n matrix and H2 is a 2n by 2n matrix. And with these answers, we need to see whether we can find a BPS solution in the theory. And this is indeed possible only if we make the diagonal entries of these matrices to be all equal. Okay, now coming to the E6 quiver, which is shown in this diagram. And instead of 2 different gauge groups, we have 3 gauge groups of 3 different ranks, n, 2n, and 3n. And in this case,
it's easy to see that you have to put those ranks.
I'm sorry.
The diagram, of course, is the usually 6 is based in diagram, but why those particular ranks?
Yeah, it is because so there's the Chern-Simons level has to satisfy a certain constraint so that these theories are in correspondence with the superconformal theory. So that constraint comes from is sum over ni ki is equal to 0. Where this I goes from goes on the rank, I mean the gauge groups of the theory. So in this case, these NIs are the data that comes from the Lie algebra, the semi-simple Lie algebra. In case of A, all Ni was 1. So we have only Un. In case of D, Ni can 2 values, Ni is equal to 1 and Ni is equal to 2. So we have Un and U2n. And in case of E, E6, we can have Ni is equal to 1, 2, 3. So that gives us 3 gauge groups of 3 different ranks, n, 2n, and 3n. So only these theories are in correspondence with a superconformal theory.
So these come from managing of the beta functional terms?
No, that I don't know. That I'm not aware of.
What are the Chern-Simons levels for each of these?
Chern-Simons levels that satisfy these constraints.
So you can choose anything.
You can choose any integers, of course. Yeah.
Any integers
That satisfies these relations. So for A, it is sum over K's to 0. For D's, it is K1 plus K3 plus K3 plus K4 plus sum over 2 times K J, where J runs from 5 to n is equal to 0. Just depends. Satisfies this relation. And similarly for E6. Yeah. Okay. Now, just like before, we can substitute these answers in our supersymmetry variations of the fermions. And we can see we also need to turn on an additional adjoint scalar phi I. Okay. And now we have found the BPS solutions in the theory. We want to find the effective action of the BPS background. So which is again done by computing the effective action of the interaction of the collective coordinate with the fermions. So now here I have written down all the interactions of the fermions with the collective coordinate, which is sitting inside phi AB. And then you substitute the answers of the phi AB that we found from the variation of the supersymmetric fermions, variations of the fermions, and equating it to 0. And then what we see is, so this last line from 5 to n, it is similar as the circular quiver. But these two lines, which comes from the external nodes, which is connected to 3 hypermultiplets, it is different. So we substitute the answers here, and what we see is there is also one cancellation happening in the external nodes, which is because of our choice of the answers that we chose, and it does not interact with the external fermions as well. So here also we are not getting any interaction of the collective coordinate with the fermions of the theory. So therefore the effective action will be that of a free particle which is moving on a sphere, and a result remains external. Is just a name. So these in between, these are like the circular quiver only, but these external nodes, I mean, they are connected to 3 arrows, right? So I'm just calling them external nodes. So just to conclude the first part, we have obtained the component action for Yang-Mills deformed ADE Chern-Simons matter theories in 3 dimensions, and we have checked that they have n is equal to 3 supersymmetry. We have obtained supersymmetry variations in these theories, and we have found classical BPS monopole solutions in the theory, and we calculated the non-abelian R charges of the monopole operators in these theories, and we have found that monopole operators in ADE quiver theories with 0 scaling dimensions. The lowest value of the scaling dimension is 0. Okay. Now we can come to the computation of superconformal index in these theories. So yeah.
There is superconformal theories with SON and H groups.
I'm sorry?
SON or SPN, those kind of H groups. These were just symmetry. So in 4 dimensions, the n equal to 2 superconformal quiver theories have this same ADE classification, but some of the nodes can be.
Yeah, SON, yes, I think there are, I am trying to think about some references.
That's the way we also get the ranks. We start from n equal to 2 in 4 dimensions, symmetrically reduced. Get the same quiver, but now we are adding the Chern-Simons term, so that's this additional constraint of that Chern-Simons. You make it superconformal even in 3 dimensions.
So you are asking whether there is a theory in 3 dimension with Chern-Simons theory with gauge groups SON or not. I think there are some paper by Nishioka where they have considered theories with SON and SP and but yeah, I have not considered.
Don't repeat what you did for monopole operators even in that.
No, I haven't thought about it.
For those that dual gauge, having a description is no?
I haven't found any. I found this for unitary theories only because Ebgm is unitary. So from there, things have been well studied, but whether it has been studied for SON or not, I'm not aware of that.
Alternate, like one node is SO, the other node is SP. This Fourier default is kind of acting with plus or minus on different heads. If I'm not recalling.
Okay. Let's talk about superconformal indices in the same theories. So let me first define what a superconformal index is. Then we'll compute the superconformal index by using the technique of supersymmetric localization. And then we'll apply this technique in case of ADE quiver gauge theories. And we'll finally do a large N analysis of that index. So superconformal index.
So since you already found the spectrum, right? Why do you again have to do localization? Can't you just use the spectrum directly to calculate the index?
I mean, that was the spectrum of the monopole operators, right? No, superconformal index is a different observable. That I just calculated the charges of the monopole operators of that background.
Yeah, and that gives the conformal dimension.
Yes, yes.
The superconformal index will probably contain those also. Because it counts all operators, right?
Okay. Oh, so you're saying because monopole is a gauge invariant operator, I mean, polynomials.
Superconformal index involves all operators.
There I did specifically for the monopole operator, but there can be other operators as well.
Yeah, that's true.
Yeah.
I mean, you cannot get the index directly from there.
Okay, so a superconformal index is a supersymmetric observable which is defined in a superconformal theory in D+1 dimension as follows: I beta j. Here the trace is over the Hilbert space of the conformal field theory, and -1 to the power f is the fermionic operator, which gives eigenvalue +1 if operated on a bosonic state, and eigenvalue -1 if operated on a fermionic state. And Q and Q daggers are some supercharges in the superconformal field theory, and TJs are the generators of global symmetry group that commutes with Q. And we can show that all the states for which the anticommutator of Q and Q dagger is greater than 0 comes in a pair of boson and fermion, and therefore because of this -1 to the power f, there's a cancellation which happens for these states for which the anticommutator of Q and Q dagger is greater than 0. Therefore, the index should be independent of this parameter gamma. So this is how a superconformal index is defined, and see how to compute this index by using technique of supersymmetric localization. So the argument goes as follows. Suppose we have a theory with an action S, which is a functional of the fields in the theory is phi, and Q is the symmetry of the action. Therefore, Q S is equal to 0 and Q square is equal to 0. And now we deform the action of the theory by a Q exact term. A Q exact term is a term which can be written in this form: T, which is some parameter, and Q, V of phi. This is a Q exact term. Now, if you deform the action of the theory by a Q exact term, then the path integral will also be deformed as shown in equation 1.32. But one can show using these two properties that the path integral is independent of the parameter T. So it is invariant under this deformation. So we have seen that the path integral remains unaffected by the deformation. So we can adjust T as per our convenience. Wherever it is convenient to do the computations, we can set T to that. And at the end, we can set T is equal to 0 because the path integral is unaffected by the deformation. The answers we obtained by any T should still be valid. So when if we take T to be very large in some theories, the theory becomes free, and the dominant contribution of these deformation parameters comes from a region of field space where QV is equal to 0. And then at the end we set T is equal to 0, and we still use the results. Okay, this is the argument of the localization, and we want to apply this localization technique to find this superconformal index, which is defined for a n is equal to 3 quiver gauge theory as follows in equation 36. So H is the cartan of the R symmetric group. In this case, it is SO3, so there is only one cartan H. Epsilon is the energy, and J3 is the third component of the angular momentum. And Q and S are the Hermitian conjugates in a radially quantized theory. Now this index has a path integral representation on S2 cross S1. So we want to find this index by doing a path integral. Okay. So, now because this theory, as we have seen before, is strongly coupled, we introduce this Q exact deformation same way as before, which is S Young-Mills and S adjoint. We need to add S adjoint also to preserve the supersymmetry. And these two terms are F terms and D terms of some superfield. So they are Q exact terms. So we introduce these deformations to the theory, and then what we do is we find the localization manifold, which is found by setting this S Young-Mills plus S adjoint to 0. So for that, we first eliminate the auxiliary fields in the deformation action and write it as a sum of squared, so that equating it to 0 is easier. So by equating it to 0, we find equation 14, which is called the localization manifold. And it suggests that we can choose a gauge field ansatz as equation 1.43, as well as turn on an additional adjoint scalar field sigma as follows. And this provides the localization manifold. Now we want to do a path integral in this background. Okay. So the path integral basically contains these 4 quantities. First one is a classical contribution, and then there are one loop determinants which comes from various component fields. The fermions are sitting in the numerator, and the denominator has all the bosonic fields of the theory. And there will be a gauge fixing term, and there will be a vacuum energy term, which can be thought of as a 0-point energy contribution in the path integral. Okay, so first let us see how to compute the one loop determinants in the theory. So we start with the matter action, which contains the hypermultiplet scalar fields, which is given in this equation 1.46. And the trick is to find the one loop determinant for this hypermultiplet matter fields is expand the fields in using the machinery of scalar monopole harmonics, which is denoted by Q, J, and M. And since we are doing a path integral on S2 cross S1, this tau is the Euclidean time and y qjm and omega is the coordinate of S2. And y qjm satisfies this eigenvalue equation given in equation 48. Now we substitute this expansion. We expand each z and w, z dagger and w dagger as equation 47 and substitute it back in the action. And we do the integration, omega integration, and after that we do the tau integration to find the determinant of the operator sitting here in equation 50. So after doing so, we find the one loop determinant of the hypermultiplied scalars in the theory, which is given in equation 52. Here f plus and f minus are some expressions involving the x's. X is e to the power minus beta, which was present in the original definition of the superconformal index. And we see that here x prime is present, but we should see that there is a precise cancellation of x prime, which comes after we compute the effective action, one loop determinant of the fermions. So similarly, we find out the one loop determinant of the fermionic matter fields, and we find this expression in equation 55. And we see that the contribution from x primed precisely cancel with the contribution of x primed from the bosonic fields. And we are left with the final expression of the one loop determinant of the matter fields, which is given in equation 58. Okay, now we need to find the one loop determinant for the other fields in the theory, which are the gauge field, the real scalar field sigma, and the complex scalar field phi and phi dagger. So it can also be done using the machinery of monopole harmonics. So if it's a vector field, we should use the vector monopole harmonics, scalar monopole harmonics, and complex monopole harmonics. So after doing so, all the contribution of the adjoint fields in the one loop determinant are given in 1.61, where f adjoint is some expression involving the charges of the Dirac monopole configuration that we found, which is given in equation.
These calculations are done in the G goes to 0 limit?
Yes, G tending to 0 limit only. Yeah. So we are considering only the interaction that survives in the G tending to 0 limit. Okay. Now, so all the determinants are done. Now we need to find the gauge fixing term. Okay, so we work in a gauge which is given by dA is equal to 0. And one can see that for Q is equal to 0, the Coulomb gauge above does not fix the gauge completely. There still exists some non-zero gauge transformation parameter for Q is equal to 0. Therefore, we impose this condition 1.64 and compute the determinant of this operator. And that comes out to be 1.65. So this is the gauge fixing term, for this gauge condition. And there is one more gauge condition that comes from dA is equal to 0 that cancels out with one of the factors in the one loop determinant. And now just putting all the results together, we see the final expression of the index in equation 66. So there is an integral over the alphas, and this is the Faddeev-Popov determinant that comes from the gauge fixing, and this is the classical term which comes only from the Chern-Simons part of the action, and these two are the one loop determinant that comes from various fields in the theory. So this is the final, and x to the power epsilon 0 is the vacuum energy. So this entire thing is the final result of the superconformal index that we defined for the circular quiver A. Okay. Now one can find, do a large N analysis of the index, which will be useful later. So for that, one need to describe, choose a flux configuration, which is described by a...
large N limit of this index is left to gravity.
Yes.
What about the monopole operator? Can the advance compare them on the gravity, something in gravity calculation? Because those are also ETS objects, right?
So monopole operators are also useful in some gravity computation, but I don't know that. But what I have thought is one can compute the same superconformal index in the gravity theory and then match the Largen limit of this index to that gravity index. So
but these will be two independent calculations. The monopole operator is presumably getting some of them, but that's just one class of operators whose operator dimension is calculated from the gauge theory side. But there must be some more to calculate the ones for the gravity.
Okay, gravity side, I don't know how this monopole operators is described, first of all. So you're saying monopole operator should be described, I mean, should be mapped to some quantity in the gravity.
Yeah.
Is that? That must be included in the superconformal index itself.
Yeah, that's true. But that's a big object, right? Monopole operators are some very specific kind of things. So those should correspond to some specific configurations in gravity.
Okay.
The index counts the full spectrum, right?
Yes. Yes. So monopole operators are also maybe somewhere included in this expression, and they should be included in the gravity side as well.
Yeah.
Okay. That I don't know how it is hiding inside the gravity side.
In the original Ebgm, also they have to postulate this monopole operator because of some maximum gravity.
Yeah, there this monopole operator specifically with the conformal dimension 0 was somehow important because so when they did the matching, they wanted some operator which involves monopoles but does not change the dimension of that operator. So that means the monopole has to be of dimension 0. So that's how the dimension 0 monopole operators were somehow important. But I have not gone through that aspect at all. So I don't know how it is important. Okay. So now it is, we want to do a Largen analysis of this index so that we can match the superconformal index from the gravity side of the same theory. And it is basically done as follows. We, for the 1/n expansion, we can choose the flux distribution, which is denoted by these set of integers q, set of n integers. We can choose them to be all 0. We can choose some of them to be 0, rest of them to be non-zero. And then we write the rank of the gauge loops as follows. Nj is the number of zeros and nj is the number of u1s with non-zero fluxes. Then we want to carry out a 1/n expansion. So we introduce a variable which contains 1/n rho r, and then we substitute this in the expression of the index, and we can calculate the index. So it is the result for the 0 flux sector, which is given in expression of I0, and we can perform the Gaussian integration. Therefore, I0 is given by the determinant of this matrix n. And similarly, in the non-zero flux sector, we can choose some of the charges to be 0 and some of the charges to be non-zero. And we see that by doing so, we end up with this expression of the index where these letter indices, expression of the letter indices f changes and is given by given in equation 74. And it says that whenever q is, suppose qn is positive and qm is negative, and by using this relation, we can show that whenever the charges are connecting, one positive and one negative, it cancels out, and therefore the index has this nice property that it factors out. The I can be a index with only 0 charges and only positive charges and only negative charges. And after we can choose q's to be some integer. I have chosen q to be 1 and 2, and then I performed this contour integral, and one can find the Largen limit of the index in some specific cases, and this result should be compared with the dual M theory index. As I said that these theories have M theory dual in terms of ADS 4 times M7. One can compute the same superconformal index that we defined in the conformal field theory side, and the index should match with the large N limit of this index. So yeah, just to conclude, we have computed the classical BPS monopole solution and their SU2R charges in a class of N is equal to 3 theories under ADE classification. We have computed superconformal indices in these theories, and it will be interesting to calculate the multi-particle graviton index of the corresponding gravity dual of these theories. And it is for some cases of this quiver gauge theories, it is well known what is the gravity dual, and compare with the superconformal index we obtained. And one can also compute a topologically twisted superconformal index. So the index we defined is the most simplest index, and one can define a topologically twisted index in the same theory by adding an appropriate background for the R symmetry, which is proportional to the spin connection, and then compute the large N limit of the index. And that index should predict the microscopic entropy of a magnetically charged supersymmetric black holes in ADS4. This calculation has been done for Ebgm theory by Benini, Ristov, and Jaffroni. And one can see if that is still can be generalized to our case. Yeah, it is. I mean, it's a big series in X's, but for some simple values of, I've done this for only these two values. It's just a contour integration which picks up. So one has to just expand these expressions, which is some series in X's, and we just need to pick up the power 0 terms in X's. It comes just from the alpha integral. I mean, it's big, but people have done it.
So if one can actually calculate the gravity index, then you can compare it.
Yes.
Are there more questions?
Hi, am I audible?
Yes.
Yeah, I have a question and a comment. Could you go to sort of the beginning of the talk where you show the explicit Lagrangians with d3x, d4 theta?
Here?
Yeah. So I think this Lagrangian is manifestly n equals 2 supersymmetric.
Yes.
And not n equals 4. And so yeah, the question is, how do you show this is, with the Chern-Simons term added, how is this n equals 3 supersymmetric? What extra do you show? You said that you have checked this is n equals 3 supersymmetric. So what extra thing do you check?
Okay. So what I have checked is, I mean, this was already shown that it is n is equal to 3. And what I have checked is this entire thing is n is equal to 3. That I have checked by simply substituting the supersymmetry variations in the action.
Sorry, what part was already shown?
So
I mean, yeah, it's known that the Chern-Simons action is n equals 3 supersymmetric if you have the n equals 4 vector multiplet. So when you say you have shown n equals 3 supersymmetry, what exactly is shown? What exactly needs to be done?
Yeah, so you have the action, you can compute the action, and you have the supersymmetry variations. You can guess the supersymmetry variation by standard method.
Okay, so yeah, okay, so 1.12 are the variations.
Yeah, and you vary the action simultaneously for all the component fields, and you substitute these variations in the action, and you see that it has n is equal to 3 supersymmetry. That's how I have checked.
Oh, can you show 1.12? So in 1.12, how many parameters are there? There are only 3 parameters or 4 parameters?
There are, G is one parameter.
No, I mean the supersymmetric part, the
okay,
curly
okay.
up.
This epsilon AB, it has 3 parameters. Epsilon 1, epsilon 2, and epsilon 3. It has 3 parameters.
Okay, so you have only taken n equals 3 to begin with, and then my question was in the knowledge that the vector multiplet is n equals 4 supersymmetric. So you take the n equals 4 supersymmetric variations, and then when you apply that variation to Chern-Simons, you see that one of the epsilons won't give 0. So I was thinking you checked that. Okay.
Yes.
Okay, but you checked only the n equals 3, which is no, okay. Okay, and one more comment. Near the end, you made a comment about topologically twisted index, and you mentioned that it has been done only for ABJM. Actually, it has been done for ADE by me and my collaborator on your end. So I think you cite us in your paper also. So yeah, ADE has been done for. But ADE, the way you have done superconformal index, the larger limit, I mean, if you write these Fs that you have in sort of Pochamer symbols, and then if you try to take larger limit of that form will be more useful in comparing with gravitational results, I guess. So yeah, I mean, this factorization result is nice, but to have a proper form which can be useful in comparing with gravitation, I think looking at the Pochamer symbols and then trying to do larger limit of that form, it will be more productive.
Okay, thank you. Thank you very much.
Okay. Thanks.
Are there more questions? So if no, let's thank Moumita for this nice talk.